Okay, we're going to look at the moment of inertia and rotational kinetic energy and what part the moment of inertia plays. Let's recall that kinetic energy, denoted by K, is given by 1/2 the mass times the velocity squared. Now let V be the velocity of an element in a rigid body as shown here, rotating around the axis marked by X with velocity V. Of course, V will be tangential to the vector Ri, which is called the lever arm. How is that tangential velocity related to the angular acceleration omega? Well, we know that the velocity is equal to the radius, in this case the Ri, times the angular velocity omega. So we can write the kinetic energy of the ith element equal to 1/2 mI squared will be equal to 1/2 the mass of the ith element times the radius of the ith element from the axis of rotation squared times the angular velocity squared. And of course we recognize that the quantity 1/2 mr squared is the moment of inertia. So in general we can write the kinetic energy of the ith element, rotational, will be equal to 1/2 the moment of inertia of the ith element times the angular velocity squared. So rotational kinetic energy in general is written as 1/2 moment of inertia times the angular velocity squared and is denoted K sub r. Now let's recall the conservation of energy equation. Conservation of energy equation for an isolated system says that change in potential energy plus the change in kinetic energy plus the change in the system energy must equal 0. We allow no energy to move in and out of the boundary. And of course the change in potential energy can be change in potential energy from gravitational forces or change in gravitational or change in potential energy from elastic forces. Change in kinetic energy now involves two parts. We have a change in kinetic energy translational, where the whole thing may be moving, and a change in kinetic energy rotational, where while it's moving, it's rotating. Or it could be simply that there's only a rotational kinetic energy. So we can write the change in kinetic energy rotational as the difference between 1/2 moment of inertia times the final angular velocity squared minus 1/2 the moment of inertia times the initial angular velocity squared. Now the question is, how do we include this term in our conservation of energy equation to actually solve problems? End of module.